Okay, so this was quiz 2, 2018. So I'm not planning on, last year we sort of had a different kind of schedule, so I don't plan to have any CT questions, so we'll just skip that. But let's do problem 2 together. So this was pretty easy. What's the Larmor frequency? So it's just gamma over 2 pi times B naught, right? And what's B naught of the Earth's magnetic field? Like half a Gauss, right? Okay. So B naught is half a Gauss. Earth's magnetic field is about half a Gauss. And we know gamma over 2 pi is, what were you told to use? 4,000 hertz per Gauss? So that's, yeah, well here it says just assume this. So let's do that for this today. 4,000 times 0.5 equals 2,000. So this would be the closest one, 2.3 kilohertz. Okay. So if you used 4257 or 4258, you'd get closer to 2.3 kilohertz. But either way, you would get close to the right answer. All right, so that's fairly straightforward. So the bottom line is all the, you guys have the solution. So I'll go through this and I'll sort of explain to you how I would do the problem. But feel free to stop and ask questions. Now I'm sitting down, so you might have to just yell out because I'm not going to be able to see you as well. All right? Okay. This one, MRI signaling artifacts, multiple choice question. What do you think the problem was? So clearly you see these stripes here, right? Let me change the color on that. So there's the stripes in the image, right? So there must be some, based on what you did with your homeworks, there must be some energy out in K space, and it's going to be out, it should be somewhere out here, right? So that then, something like that, okay? So let's see, what was the answer for this? Was the answer none of the above, I think? Yeah, none of the above.
I have a question for this
yes.
problem. For A, for example, how would that look like? Would that just like result to aliasing?
Yes, that's right. That would lead to aliasing. Okay, very similar to the homework problem you had.
Can you explain that again with A? Like, what does the wording mean? Loss of readout data from every does that mean that you're not taking?
Yeah, it's exactly like the MATLAB problem you did where you zeroed out every other thing of K-space, right? You're basically missing data, right? Yeah, question?
So what is the error, the readout, or the collecting error here?
Sorry, what is the problem?
Yeah.
Oh, the problem was that there was a spike in K-space. So for example, let's say you left your door to your magnet room open and there was some energy that got in just at that time that it was going through that part of K-space. That would give you a spike in K-space. So in fact, if you ever have an MRI done on you and you see this artifact, then you actually can tell what happened. Like there was some spike, and it can be just even like two wires that just are like hitting each other. It doesn't require much energy to just give a little bit of energy.
Why does the spike not affect every point but only every other line?
Well, if you zoom in on this, it's basically, it's showing, it's all it is. It's sort of like this sinusoidal pattern, right? You're seeing like the peaks and valleys. So very similar to some of the examples we did in class. Or I think you guys did examples like this in your homework, right?
Yeah.
Did you put a spike? Yeah. So that's exactly what you're seeing. You're basically seeing sort of an oscillatory pattern.
This is very similar to like some aliasing effects too, right? Where you have thought we had some problems. This sinusoidal pattern because of aliasing.
No, aliasing in MR corresponds to replication of the image. Okay. Yeah. So when in MR we're sampling in K space, so we're multiplying by a comb function in K space. That leads to convolution with a comb function in image space. So that's always replication of the image. Okay. So that's how you know it's aliasing. Yeah.
How much of an explanation are we expected to give as opposed to just answer? So we have to give an answer in this kind of problems, and then you have to go like write something or?
Yeah, like a one. Generally, if it's an open response, I mean they're very short. It's like you could just even draw that picture. Yeah. Question.
So in noise speed, it would say, or it says we have two spikes, one at k what, or ky equals 0 and kx equals 0. Would you have two sets of lines?
Yeah, and one would be horizontal and the other would be vertical, right?
Okay.
Yeah. So that's how you know it's not that one. Question back there, or you're just knitting? Okay. Okay. Yeah.
Okay, it's like for option C.
Yeah.
For option C to have been the answer, would it have just been like a much smaller object because the field of view in the y direction is higher, sort of in stretch?
So I didn't come up with this question. So, but that means that basically you'd only be acquiring half of k space, right?
So that means that your field of view in the y direction is going to be double, which means it's going to be stretched.
No, because remember, field of view. I mean, you're still acquiring this. So the delta k is ky is unchanged, right? So your field of view would be the same.
Okay.
This actually, the real answer is the image might still look okay because we didn't really go into this, but real data tends to have what's called Hermitian symmetry. So the top and bottom of k space are sort of similar. So so the actual image will look very similar to what you're getting.
So the only thing lost is resolution then, maybe?
Well, we didn't really get into signal noise ratio, but you would be losing some signal noise ratio because you're collecting less data.
Okay.
Okay. All right.
One last
Yeah.
question. In regards to the spike, what if we had the opposite of a spike? Like, let's say this one point, I guess, in our, or like loss of information at 1 pixel. Like, how would that affect the image? Like,
That would be much harder to see because it depends on like if what you're losing, let's say that the value was very small anyways and you lost it, it wouldn't really have an effect. Now, if you lost it at the center of k space, it'd have a big effect, right? So it depends on how.
where we are.
Yeah.
And that would affect the image by like having this lines, or will it not just? There be no lines or patterns.
No, there wouldn't. It would be more like those things where we blocked out parts of k space,
Okay.
right? So it'd look more like that. You're losing that information. So the image would not have the information in that part in k space. Yeah. Okay. So this one here, let's see. I'm actually going to skip this one because we're not. I'll just say we're not going to have anything like this on this. And if given the time constraint, we probably need to move on. Okay. All right. So let's move on to the other ones. So this one is the magnetic field is 1.5 Tesla, right? And we have spins at 0 and 5 centimeters in the presence of 2 Gauss per centimeter gradient field. If the spins are in phase at time t equals 0, what is the earliest time at which the spins will be in phase again? Okay. So really, does the 1.5 Tesla matter at all? No, right? Because it's the relative fields that matter, right? So the delta B between those two spins is going to be 2 Gauss per centimeter times 5 centimeters, right? So there's going to be a 10 Gauss difference in the B field between those two, right? Okay. And then we also know, so we know that the change in frequency is just going to be the gamma over 2 pi times delta B, right? So that's 4,000 hertz per Gauss times 10 Gauss. So I have 4 times 10 to the 4 hertz. Okay? So that's my frequency. The frequency difference between those two spins is that many hertz. So I need to wait for 1 cycle for them to get back into phase again, right? So that would just be, the time is just going to be 1 over delta F, which would be 0.25 times 10 to the minus 4, right? Equals 2.5 times 10 to the minus 3, or 25 times 10 to the minus 6, right? Right? So it's 25 microseconds, is that right? That's the answer to that. Should get the answer now. Okay, everyone okay with that?
Does that S like the bandwidth basically from 0 to 5?
No, delta F is the difference in procession frequencies.
No, I know, but then would it also be equal to, if you're picking the bandwidth, would you have to do the same thing?
No, right. If you wanted to, right, the bandwidth, right. If that's what you only want to excite spins between 0 and 5, that would be the bandwidth. Yes, that's right. Okay. Any questions? Okay. Part 6. You're asked to design a set of gradients that take you to kx equals 2 inverse centimeters and ky equals 4 inverse centimeters. The maximum gradient you have available is 4 Gauss per centimeters. What's the minimal temporal width you can use for these gradients? First of all, which is going to determine that width? Is it going to be kx or ky? So which is farther out in k space? Right. So it's going to take longer to get out there, right? So if I have a maximum gradient available, I want the thing that's going to determine how long it's going to be the ky. So I know I want 4 Gauss per 4 inverse centimeters equal to gamma over 2 pi times my gradient times my time, right? Go ahead.
Let's say maximum gradient amplitude, is it the upper limit for both GY and GX?
Yes. Yeah, if you're not told otherwise, that's how, when people talk about maximum gradient amplitude, it's for each axis can go up to 4. Yeah, that's a good question though. Okay, so then we say T is equal to, this is Gauss per centimeter, let's see, 4 inverse centimeters over 4 Gauss per centimeters over 4,000 Hertz per Gauss. And the 4's divide out, right? So I'm left with, what is it? 0.25 times 10 to the minus 3, is that right? Minus 4? Okay.
Oh, yeah, right.
Which is equal to what? B. All right? Okay. 7. You're asked to design a spin warp gradient to achieve FOV of 20 centimeters and resolution 2 millimeters. The maximum gradient strength available is 2 Gauss per centimeter, and the readout sampling period is 5 microseconds. What should be the amplitude of the readout gradient? Okay? So this is a spin warp. So let's think about it. So I have FOV and resolution. Which one matters for this question? The FOV, okay? Because it's the delta K that matters, right? So remember, we have this readout gradient here, right? And we're trying to actually figure out its amplitude. We have some delta T, so what we want to do is figure out what that area needs to be, okay? So we have gamma over 2 pi times G times 5 times 10 to the minus 6 should equal 1 over inverse in that, right? Okay, so I can just solve for G. It's equal to, let's see, 1 over 20, 5 times 10 to the minus 6, and then we have 4,000. Right? Okay. And we already did this in class, I think, right? So that gives us 2.5 Gauss per centimeter. So C class notes. So it's F. Right? Okay. Did we already do this one in class, number 8? I don't know. Maybe. Okay, well, let's do it anyways. For a spin warp pulse sequence, you're asked to design phasing cogradient to achieve FOV of 20 centimeters and resolution 2 millimeters. The maximum gradient strength is 6 Gauss per centimeters. What is the minimum width you can use? Okay. So we did do this. Right. Okay. Should we do it again?
Yeah.
Okay, let's do it again. Yeah, how far out do we need to go in K space, right? So we need to go out, so WKY is equal to 1 over 2 millimeters, right? And let's get into centimeters. So that's 1 over 0.2 centimeters equals 5 inverse centimeters, right? But remember, we're going either the positive or negative gradient, right? So let's make our life simple. So ky max should just be 2.5 inverse centimeters, right? So that's as far out as we want to go in k space, okay? And so now we can say, well, then that's just going to be equal to gamma over 2 pi times my 6 Gauss per centimeter times my time. So t is going to equal to 2.5 inverse centimeters over 4,000 over 6. Okay? And I think that gives 104 microseconds. So the close answer is 8. Okay. So here's one that we haven't seen before, which is based on stuff we did last lecture. So consider a vial of liquid with T1 equals 2000 and T2 equals 2000 at room temperature in a 3 Tesla magnetic field. You cool the temperature of the liquid to 10 degrees C, so it went from 20 degrees C to 10 degrees C. What are the most likely values for the T1 and T2 of the cooled liquid? Okay. So what do we think happens with tumbling as we cool? Right. So we're going to have less tumbling, right? Okay. So what should happen to the T2? Should it go up or down? Down. Okay. So the only ones that go down are these guys, right? Okay. So now we just have to say now which one of these three has to be wrong?
The one with T1.
Yes. So it's wait. Well, let's see. I guess they could all be correct, right? Okay. So it's asked for what are the most likely values of it. Okay. So so we're told it's a liquid, right? Okay. So do we think that let's see. So which of these do we think? So remember the T1 things as a function of tumbling rate are like this, right? Tumbling rate.
At the very bottom is more of a gel.
Yeah. So here I think the answer was saying we're most likely in this regime here because it's a liquid. So as we cool it, the tumbling rate is going to go down, and so therefore we're probably moving along this thing. And so then we would, if anything, we would expect the T1, I guess, to go down. Okay. Now I have to say that's sort of more ambiguous than I would like for a question like that, but that's the way it was last year. Okay. Right. Okay. Any questions on that? Okay. How many of these do we have? Well, there's only 12 of these. Oh, that's good. Okay. Dr. Block designs an inversion recovery sequence with inversion time 1000 and TR equals what?
Sorry, I just have a quick question in regards to the previous question.
Yes.
So if we picked D, would that be wrong just because T1 is larger than T2?
D?
G.
Oh, G.
Would that be wrong?
No, because T1 is always larger than T2. I mean, in general, you always have T1 is greater than or equal to T2.
Is it possible that T1 didn't change?
It's really probably not that possible because you're always going to be moving somewhere on that curve. So I guess this one, the G, you could probably argue is not correct. So you're just trying to decide between whether H or I is more likely. And therefore, you're trying to decide, are you here or are you here? And in that case, you're more likely to be here if you're given a forced choice. Okay?
Is it normal that we have T1 equal to T2?
It's much greater than T2, but it can, in some places, it could be, it's always going to be a little more than T2 because T1 can give rise to T2. Yeah. So in this case, I mean, it's a problem. It's a homework problem. It's a quiz problem. So that is sort of the most likely answer. Okay. Okay. Number 10, Dr. Block designs an inversion recovery sequence, and he adds some gelatin to the liquid. What new parameter should Dr. Block use to null out signal from the modified liquid? Pick the best answer. Okay. So remember, the parameters are we have an inversion time, and we also have, so this is the 180 pulse, the 90, this is the inversion time here, Ti, and then the time between the next repetition is Tr. Okay. And I believe in this thing, you are actually given the formula, right? This inversion time. Right, so that's you'll want to make use of that. Okay, so in general, we don't expect you to remember that formula. So if you need a formula, we will give it to you. So let's see what we. So the first thing to do is to figure out what we expect to happen with T1. So what do we expect to happen to the T1? So we're not really told what the T1 is to begin with, but do we expect the T1 to go up or down? Yeah, we expect the T1 to go down, right? So it went from a liquid to a gelatin, right? Okay. So we're moving sort of from here to here along the curve. Okay. So then the question is, so let's say we go back here and to this thing. So now we know that the T1 goes down, right? So this thing here, this T1 goes down, right? And this T1 goes down as well, right? So if we want to keep things nulled out, if we want to keep this, let's see, adding the gel, reduce the inversion time. Yeah, so I think the require TR greater than TI. Okay, so let's rule out the ones that don't make sense. So these ones just don't make sense, right? Because the TI can't be greater than the TR or equal to. So we can just roll these out immediately. Okay. So then we're just left with, and then look at these. The TR has stayed the same. Okay. So whoever designed this quiz made it easier for you. Okay. So TR is the same. So now you're just trying to discuss whether the TIs are going to go up or down. Okay. Yeah, the TRs all went down, but they all went down the same way, right? They all went to the same value, right? So you're only looking at whether the inversion time. So the TR went down, okay? So the TR went down and the TI went down, right? The T1 went down, right? So both TR and T1 went down. So maybe let's just assume this was approximately the same, right? You know, so let's say this didn't change, right? It's approximately the same. Because if TR went down and T1 went down, let's just say, as a guess, maybe the exponential term doesn't really change very much. And then let's see if that gives us the right solution. So then the T1 went down, but it's a minus, and then let's assume and that the log is going to be a negative term. So the T1 went down, so therefore we would guess that the inversion time would also have to go down. Okay, and then of those choices, that's the only one that has that. So it'd be C. The what? That's because.
And if that was not one of the choices, then what was the reason?
Well, the real reason is when I designed this problem, I tried different values of TR and came it so that it would be easier for you. Yeah, but in general, yeah, you would have to. I mean, if you had MATLAB and stuff, you could look at all the different choices. But in this case, it's basically D through F are just incorrect on first principles. Therefore, you're left with an easier problem. Question?
You say again why by looking at the formula we get that they are both going down. So.
Well, we know that T1's going down, right? Because we added a gel. And you know that 2000 to 1800 is a decrease as well. So you know that TR is going down and T1 they're both going down. You don't know how much. So as a first guess, you might as well assume that, let's say they're going down about the same amount. And then, yeah.
So we kind of work on this problem with like a process of elimination. If we don't have that, is there a way we can tell the trend of TI and TR?
Yeah, I mean, I think if you read the notes, if you held the TR constant, right, you could do, even if you held the TR constant, you'd still have to reduce the T1, right? Because let's say, yeah, but I think that the problem is designed so it doesn't force you to think, it's designed to be a little easier than it would be if it's open-ended, right? So I think the thing to think about is, when we're coming up with multiple choice, so the test taking skill is, you have to realize that to make the quiz will have certain things built in to make it so it's easier to decide. And so maybe think about it, but don't overthink it, is the best advice I can give for multiple choice. So first of all, look and see what has to be wrong because it's just nonsensical. There's always going to be nonsensical answers. So in general, that will allow you to, I'll get to you in a minute, allow you to get rid of half the answers. And then of the ones that are remaining, then sort of work on those. Okay. I would not recommend, looking at every single answer one by one. I would sort of first recommend get rid of those that just have to be wrong. Okay. Otherwise, it's going to take too long for you to do the quiz. All right. Question back there.
So the condition is that TR has to be greater than T1, so like F would be an option. It's not a greater or equals thing.
Yeah, so if TI is, well, even if it's equal, it doesn't really make sense because then the inversion pulse would line right up with it. Yeah, so none of those make sense. And so those are put in because they just don't make sense, but, it's sort of, yeah, okay. So number 11, consider a slice selection pulse of the form A sinc T over T, where T equals 400 microseconds. Assume we use a slice select gradient of 1 Gauss per centimeter. Now we increase T to 500 microseconds. What should be the new value of the slice select gradient to keep the slice thickness the same? Okay, so once again, we care about bandwidth equals gamma over 2 pi gz times delta z. Okay? And if I increase the T from 4 to 500 microseconds, is bandwidth going up or down? It's decreasing, right? So the bandwidth goes down by how much? Yeah, it goes down by, so the bandwidth in one case, the original bandwidth was 1 over 400, right? And then the bandwidth goes to 1 over 500, right? So it's basically the bandwidth decrease, the overall bandwidth goes down, it's a factor of 0.8, right? Okay, so my bandwidth has gone down by 0.8, right? So to compensate for that, I better have my GZ, whatever 0.8, 0.8, I want to keep this delta Z the same, right? So if bandwidth goes down by a factor of 0.8, then GZ should also go down by a factor of 0.8 in order for delta Z to be the same, right? So I had 1 Gauss per centimeter, so that means I'm going to go down to 0.8 Gauss per centimeter. All right, everyone okay with that? Okay. And then finally, consider a spin-more pulse sequence designed to achieve an FOV of 20 centimeters in both x and y directions with 1 meter resolution in both directions. Maximum available gradient is 2 Gauss per centimeter. User reduces the FOV in the x direction to 10 centimeters, but keeps the matrix size the same. What will we need to change in the pulse sequence? Assume ADC sampling period is not changed and all other parameters are held constant. You may pick more than one option. So this is actually sort of difficult because you're told that you might pick more than one option. So now you're like, oh, is there one option, 2 options? So these are a little tricky. I think that's the only one of that kind, so I wasn't too cruel last year. So let's first of all rule out the things that don't matter, right? So he reduced the FOV in the x direction. So right off the bat, do I need to worry about phase encode? No. So I get rid of this, and I get rid of these. Okay? Yes?
You keep the
The matrix size is how many voxels by how many voxels the image is. So if it's like a 64 by 64 image, it stays 64 by 64.
Oh, so you change the resolution.
Well, so that's the thing. So if the FOVX,
The FOV Y doesn't change basically.
right, everything else stays the same except what's there, right? So we know that I didn't change anything in the FOV of Y in the Y direction, right? So I can ignore the phasing code. Yes.
So basically, if you're keeping the voxels in X the same,
Yes.
you have to play with your FOV and your resolution. So that
Yes, right. Because FOV went down by how much? 2, right? Number of the resolution, the matrix size in X stays the same, right? So the resolution also went goes up by 2, right? Yeah, remember because the resolution is just FOV of X upon number of voxels, right? Okay.
Yeah, so that's the goal.
Yeah, so this is the same, right? And this went down. Oh, it goes down. Sorry, it goes down. Yeah, sorry, yeah, right. Resolution is smaller, right?
Yeah, that's
Yeah, sorry about that. Delta, let's say delta X goes down by 2.
yes.
Okay, better resolution, but delta X is smaller. Yeah.
But if we want to keep Y the same number of voxels as in X, like the number of voxels in Y and X related to the same, then in that case, don't we have to change the value of resolution Y too? Or am I
Well, the user is not changing anything that has to do with Y, right?
oh, okay.
Right, he's not changing anything, so we don't have to worry about the Y direction. Okay, so the resolution, the original resolution, right, was 1 millimeter, right, and then it's going to go down to 0.5 millimeter, right? Okay. So let's think about other things that we can just rule off the bat. Can E be correct?
The number of unit symbols shouldn't change.
Right, because you're told it can't change, right? Because the matrix, you're told the matrix size stays the same, right? So E and F are also wrong. Can't be true. Okay, so now you're only down to 4, right? So I think that's why I'm suggesting these questions allow you to get rid of most of the answers without thinking about it too much, and then devote your first phase to get rid of the nonsense answers, so you can devote your time to the ones that require some thinking. All right? Okay. I mean, multiple choice questions just have to be written in a certain way. So that's, if you're the test taker, you just want to realize that the person making up the test has to sort of make it up in a certain way. All right? Okay. The length of the readout gradient will double. The length of the readout gradient will be halved. The amplitude of the readout gradient will double. The amplitude of the readout gradient will be halved. Okay, so let's think about which of these has to be true. So the length of the readout gradient. So will that change at all? Well, that's not the correct. Well, it's because the matrix size has stayed the same. So the number of, if F and G are wrong, can't be right, then also G and, if E and F can't be right, then also G and H can't be right. Because the delta T, the sampling period 5 microseconds is not changed. Yes.
What do you mean length? Like what is it?
Like, this is the length, right? Tau sub x. Yeah, the time. Yeah, duration. So these also can't be correct, right? So really, you're just down. You have a 50-50 chance. So the question is, right? So after all that work, you're down to a 50-50. You know, everything else has to be wrong. Okay? Because the sampling period is not changed. Okay? So if I was going to give you a test taking strategy, I would say list down every parameter that you think might be thing and just try to say, is it changed or not changed? Because that's what you're looking at. Okay? And those are the sort of same things you do in if you're doing research in MR or any field. You're always saying, okay, something happened here in this image that looks different. What stayed the same and what was changed? Okay? Yes?
Sorry, so the resolution has, or sorry, delta X has gone down by 2. which means that the WK would have gone up by 2, right?
Yep.
In the x direction, which meant that the kx max, individual kx max values are also increasing.
Yeah.
By 2. So that means that the length, the horizontal length of that k space is going to increase, right?
Yeah.
So that means, and then if, so doesn't that mean that that's the length of the readout period, right? That's
No.
okay.
Why not?
Well, I mean, doesn't it take longer to?
So what determines going from this minus kx max to kx max? What's that related to in the readout? Is it the length of the readout, or what is it? What parameter matters? So remember, I have this readout gradient, right?
Yeah.
What matters in terms of how far I go in k-space? The area. That's right. It's the area that matters. So it's a rectangle, so you can change the area by changing the width or the height.
Oh, but since you said that, well, the sampling period is not changing.
Right.
You assume that.
So basically, you know that delta k must go up by a factor of 2, right? And delta t is the same, so therefore the amplitude of the gradient has to double, right? So it must be I.
No, the delta t is the same, but because the total time, which is delta t to the number of blocks,
Is the same too.
is also the same.
Yeah, so everything works out.
Yeah. There's just a lot of moving.
Yeah, but it's basically you have to just work your way through the things that can't be true. Yeah.
I have a question.
Yeah.
So in regards to the number of readout samples,
Yeah.
will that only be affected by the RF signal that we input into our system?
No, that's determined by the fact that the matrix size is the same.
So how would we change the number of readouts if we reduce or increase the number of matrix size, and if we affect both tau and time as well? Because I know that there's an equation that relates to the number of samples, tau, and time, the individual, like.
Yeah, so basically the main thing is these are related. The resolution is equal to the FOV over the number of samples.
Okay.
Yeah, right. So if you have like an FOV and then you know how many samples you have, then the resolution is just this divided by the number of samples. Yeah.
So the number of times we apply the RF pulse, does that decide the number of phasing co-samples we have?
Yes.
Oh, okay.
Yeah, so for spin warp, every time we apply RF pulse, we get one line in k-space. And then we go line by line by line. Okay? Okay, so we have 10 minutes to go over the last one. So let me just sort of, so we're not going to have time to go over every possibility, but let me just go through a few of them so you get a sense of what it is. And then the solutions are there, and then if you have more questions, we can always revisit them on Monday. Okay? So the first thing is, you're given all these different phasor diagrams, okay? And you have to say where in k-space you are. So let me just work through a few. Let's do the top row, because I think if you get the top row, then that should be sufficient, okay? So A, let's see, A is really easy, right? Where are we in k-space? Right. So the clue here, and one thing, I mean, I will make these so that they're easy to read and it's not meant to trick you, but you do need to realize x is going this way and y is going this way, right? Okay, -4 to 4, -4 to 4. Okay, so don't get confused by that, because otherwise everything will be the wrong sign. All right. So let's look at this one here. So we'll zoom in on this one here. So what is the period in the x direction? So this is like 3 and 3, right? So it's 6, right? The period is 6, and so that means we must have kx equals either plus or minus 1 over 6, right? So is it kx plus or kx minus? Plus, right? Because we're going clockwise in the x direction. Okay. Now what is the period in the y direction? It's also 6. And is it plus or minus? It's plus, right? So B would be, yeah. So B is, yeah, so 1616, right? So that's correct. Okay. So do we want to do one more? Okay. So let's look at C. Okay. So C, what is the period of C in the x direction? How long does it take to go one cycle? 4, right? So it's 1/4, right? And why is it negative? It's going counterclockwise as I go, right? So it's negative 1/4. And K sub y is, what's the period there? Okay, so the period there is it 4? The period? Period is 4, right? So it's 1/4. And is it positive or negative? It's positive, right? Because it's going clockwise. Okay, so minus 1/4, 1/4 is C. Okay, so basically everything looks like that. Yeah.
What is the difference between H and F?
H and F. Let's see. Okay, let's do them. So H. Yeah, go ahead. Yeah. Yeah.
So are we measuring the rotation from 0, 0? Or from like...
It doesn't matter where you start. It actually doesn't matter where you start from, but 0, 0 is a good place to start from. Okay. You're just looking as you move along X, are you rotating this way or that way? So it actually doesn't matter where you start from, but 0, 0, from test taking point of view, it might be good to have a way. You want a strategy for doing all these problems so that you're not coming up with a strategy in real time, right? So if you decide 0, 0, then you always, yeah. And that will save you time because otherwise you're using that time to come up with your strategy. Okay. All right. So we want to look at the difference between F and H, was it? Yeah. Okay. So the period here is, what is it? Oh, why isn't it letting me do anything? Oh, here. Okay. The period is 2, right? So kx equals, and we're not sure if it's plus or minus a half, right? Okay, is it the same thing with ky?
No.
Okay, ky is equal to what? Okay, negative 1/4? Okay, let's see. Okay, and then here, kx is still plus or minus a half, right? And ky is what? Is it the same? Okay, so this must be a bug in the quiz then. Is that right? Is it clarified in the solution? There was an error in the highlighted line. The MAC coordinate should have been minus 1/3, 1/4. Okay, so what was, let's see. F was minus 1/2, minus 1/4, and H was 1/2, minus 1/4. Okay, so H and F. Yeah, that looks like a mistake because you really can't tell the difference. Is that right?
Yeah, because if you look back at the table, we're given 1/2 and negative 1/2, so there's no way to tell which one's which.
Right. Okay, so I think that's a mistake. Okay.
We choose which one is which.
Yeah, I don't remember what we did last year, so minus 1/2, minus 1/4, 1/2, minus 1/4. Yeah, at least for now, it looks like a mistake. But let me think if I can. Is there a reason? Let's see. No, because they look exactly the same along ky equals 0, right?
Yeah.
And then along the. Wait, are they exactly the same pattern?
Yeah.
Oh, okay. All right. Well, then they're the same. So you would have been right either way. So actually, maybe that was the intention, that you could be right either way. I don't know. I can't remember. Okay. So let's not worry about that. Okay. So then the next thing was for each object, pick the phasor pattern that will maximize the magnitude of the Fourier transform and provide the value of the vector sum. Okay. So let's look at this one here. So this one obviously has to have, it's a diagonal pattern, right? So it has to have kx equals y and ky equals y at some period. So the period here is obviously 4, right? And the period here is 4, right? Is that correct? So it has to be, I guess it has to be C, right? Because that's the only one with 1/4 and 1/4. Does everyone see that? Okay. So I think on the exam, if I remember correctly, were you given, I think the exam actually, the blank exam actually had things where you can fill in arrows. Is that right? I don't remember. Did it not? Okay. So anyways, we know that C is that one, right? Okay, so it's got to be that one. And so then what you would do is you would just sort of, you know that everywhere, you can ignore the zeros, right? Those don't count, right? And then if you look at this pattern, it's all ones along here, and it's all negative ones along here, right? So you know you just count up the non-zeros. It's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 20, 25. This vector sum is equal to 25. Everyone see that? Because all along here, these were pointing this way, right? And then along here, they're pointing this way. But when that arrow is multiplied by -1, it becomes a 1. Yeah. So you just add up all those things. So that's actually fairly easy to do. Okay, any questions on that? Okay. Object 4 seems a little more complicated. Let's look at this. Yeah, so this period is obviously 2, right? And then what's going on here? What is this period here? Is it 4? Is that? Or what is that? Oh wait, how's this drawn? Let's see. Okay, so I have -1, -1, -1, -1, and then this period is what? Is it 1? So this is -1.5 to 2.5? So that is 4, right? Okay, so that is 4. Well, I'm looking here. The middle of this is at -1.5, right? And the middle of this is at 2.5. So that distance is 4, right? Okay. So yeah, so what did I, let's see, what did we do? So we know it has to be, it could be either F or H, right? Because F or H has the -1/2 and -1/4, right? Okay. So if we look at F or H, and those are turned out to be exactly the same pattern, then we have, let me change the color here. So that was like this, right? And then it went this way, right? So what is that going to sum up to on every row? So these cancel out. Or is that right? Are they 0? No, it's not going to be 0. They're not going to cancel out, right? They add up, right? So every row is going to add up to what? 1, 2, 3, 4, 5, 6, 7, right? It's going to add up to -7. Is that right? Okay. And then what's on the next row? It's just, is it the same? So we've got this, right? So now we're going to have, this is going to add up to something with the J, right? So it's going to add up to what? -7J, is that right?
Yeah.
Oops. And then what happens with this guy here?
Sorry, what are you, is this like you're multiplying it with the C pattern, or?
Either H or F is the same, right? Because it's got to be, it has Kx equals 1/2 and Ky equals 1/4. Yeah, okay. So then here we're multiplying by whoops, this, right? So this is going to be what? Also minus 7j, is that right? Or no? Okay. Okay, so I think what happens is you have 3 of these you're gonna have 3 of the minus 7 ones. So you're gonna get the sum is gonna equal minus 21, and then you have 4 of the minus 7j's, and it's minus 28j, right? Okay, so that's a lot of work for 2 points. So that's why it's the very last question. Okay, so that probably should have been more than 2 points. So I'll keep that in mind.
So you explain base, how do we choose F and H, and then on the other one, the C or whatever?
Yeah, but basically because if you look at it's by process of elimination. Those are the only 2 that have those. You know, once you've done.
Sorry, I guess I forgot what the original question was. That prompted us to define C.
Well, basically, this is an object, right? You're trying to maximize the Fourier transform with this see where the Fourier transform is optimized. So you look at what's the period of the object, and then go to that point in K space.
Okay.
Yeah. Okay. So are there any last questions before we end? Okay, if there's no questions, that concludes this session.